Hi, everybody. As you can tell, I'm an American. I've never given a talk in England before, but my friends have assured me that if I'm doing very bad, that you'll all be very polite and not say anything, and that if I'm doing very well, you'll do the same thing. So I'll take your silence as approval. As she said, I'm head of data science at Codecademy. Before that, I was actually writing the data science, data analytics curriculum at Codecademy. But before that, I was a scientist working in computational biochemistry. And coming from a hard science background to a more computational data science background, I've been a little bit disappointed. And so that's why I wanted to give this talk, so that we can all learn together about best practices for hypothesis testing. So first I want to just give a brief overview about why we would even want to learn hypothesis testing. So classic example from my previous line of work, if we're testing a new drug and we want to know, say it raises good cholesterol and we want to know if the new drug is better, we see a difference, but how do we know that that's a real difference? Now in my current job, I work a lot with product data. So for instance, subscriptions. If we see a drop in the number of subscriptions, how do we know if that's a real difference or just statistical noise? And the reason that this is a problem is really not every difference is significant. So this was just a chart I made in Seaborn using NumPy. And as you can see, all three bars were generated from distributions with the same mean and standard deviation, but they still can look quite different. So this is why we need to test. So one of the big misconceptions that I see a lot is people don't know, or they misuse the term significant. What does it mean to be significant? So the definition, and we're going to go into this a lot more because this doesn't necessarily mean anything to people, is that the difference we've observed probably isn't due to chance. We'll get into that probability part of it a little later. But where I really see a lot of misunderstandings is when we talk about not significant. A lot of times I'll be working with a product manager who's running an A/B test, and he'll come to me, it's always a him, he'll come to me and say, I've been running the experiment for the sample size that you told me I needed to run it for, and it's not significant yet, so let's run it for another 2 weeks. And that's very bad. You shouldn't do that. Not significant is fine. Non-significant means that your variant, the experiment you were running, just isn't as good as you think it is. And there is no difference with the control group. As long as you've run your experiment for long enough, it's fine for it to be significant. It doesn't mean you did something wrong. Fun fact, this is almost always an interview question that we use. So if anybody's interviewing for data analysis roles, hopefully you'll be asked this. So I wanted to take a moment and just ask all of you, why did you come here today? What is it that you want to learn to hypothesis test? So does anyone want to share a scenario? I'm not seeing hands. Okay.
I'm using SciPy to test A/B testing
Mm-hmm.
on our website.
Okay.
So I came across because I wanted to test the significance not with the relative numbers as
Mm-hmm.
it is for, conversion rate,
Mm-hmm.
but for absolute numbers as like difference in revenue or margins.
Excellent.
So that's why I came across with the SciPy and uses the Wilcoxon test
Mm-hmm.
for our T-student.
Mm-hmm. Students T-test, we'll definitely be going over that. Anyone else have an example of when they'd think they might like to use hypothesis testing, or did you all just run in here sort of randomly? We don't have food, so I know you're not here for the food. Okay, so I'll talk about a few different examples. Obviously, drug development was where I used a lot of hypothesis testing. A/B testing. Does everyone know what A/B testing means when we say that? Okay, so I'm just going to, just in case, A/B testing is when we have two versions of something. Maybe we've made two different versions of our landing page, and we want to see which of those versions leads to more people signing up. Other examples, I used to work at an education technology company where we made adaptive learning smart textbooks, and we wanted to see if those textbooks were actually making students smarter. So we had to do a randomized controlled trial. We gave half the people a regular textbook, half the people a smart textbook, and then gave them a test at the end. And a big question that we always had is, how big of a class do we need? Can we run this in one single class of 30 students, or do we need to run it across an entire school with hundreds of students? Okay, so hypothesis testing. So as you pointed out, it can be very difficult to know which hypothesis test to use. So first of all, let's go over really quickly what it is. A hypothesis test is a way of reframing our qualitative question, is this difference real, into something much more mathematical. We're trying to figure out what is the probability that the difference is due to chance versus not. And so what we're trying to do, if anyone remembers back in college math, when you learned about proof by contradiction, we're trying to do a proof by contradiction. We start by assuming the null hypothesis, which is that there is no difference and that what we're seeing is just random. And then we pick one of these tests, and the goal of all of the tests is to generate a p-value. And the p-value is the probability of the null hypothesis. And generally, it varies a lot by what you're trying to do, but generally we want the p-value to be less than 0.05. And that's how we know that we're doing things correctly. Anyone have any questions? Cool. Okay, so how do we pick which hypothesis test? This is, I think, the reason why everyone is actually here. So this is going to be a very broad overview. I wouldn't take this to a statistics midterm, but I think this is quite good for anyone who's working in industry and running different types of tests. So the first question you always ask is my data categorical or numerical? So numerical data is something like revenue. It's something where there's actually a bunch of numbers, and you tend to have a lot of samples. So for instance, you know how much money you made every single month, and those are going to be your samples. Or you have, the heights of all the students in a class, and you want to compare those. Categorical data, which I actually find I work with more frequently, tends to be things that look like percentages. So the categories are, did I buy the product or didn't I? Did I click a link or didn't I? And it can be really confusing. A lot of people will sort of try to use a t-test on that categorical data. They'll be like, oh, but how does that work? Because all I have is one number. I have the percentage. 75% of people purchased my product. 20% of people opened an email. So that's important. The next question is, how many samples am I comparing? And by samples, I mean not like the individual samples, but like how many groups am I comparing? So there are tests for one sample versus some theoretical number. So this works either really well for if you have some sort of target, like if you say, in my OKR planning, they said that I have to get, at least 30% of people clicking this link. You're comparing whatever number you actually got to that theoretical 30%. There aren't multiple 30%, there's just one. It can also work well if there's a known number in the literature that you're comparing against. So maybe if people say, well, the average height of an American woman is 5'4", so I'm going to compare the heights of everyone who I've measured to that 5'4" and see if they're different. Two sample means you have two samples. It's probably the most common thing. And then sometimes we'll have more than two samples. Sometimes, we'll have 3 variants of an A/B test, or we'll have 3 different populations that we want to compare. And it turns out we'll actually need a different test for that. So this is probably the most important slide of this talk. This is just a table that helps you know which of your tests you want to use. I'm not going to read through the entire thing because I think that would be boring. But if you're taking notes or if you're taking pictures, this is probably the important one to take down. Okay, so people who were here early heard me say this. We're going to practice now, and we're going to practice using Codecademy. I promise I am not just shilling for Codecademy. I really did try to think of a way to do this talk without using it, but I realized I would have had to make like a big Dropbox link, and we would have all had to download things and load them into Jupyter Notebooks, and it would have been a mess. So we're going to let Codecademy do the hard work for us. So if everyone could just take a moment and follow that link to this course, that would be lovely. If you want to type in the whole long link, you can. Otherwise, you can type in the short link. And if I do this properly, I'm going to be switching back and forth between the slides and the link. Okay. Yeah, I am still there. Yeah, that's big enough to see. Pardon? Oh, go back to the slide? Sure. I have a little timer up here, so I'm going to give you guys 30 seconds to follow the link. Does that sound fair? Huh? Pardon?
Will the slides be available after this?
Sure, why not? How do you guys want me to make them available? Slack? Okay. I will have to join the Slack channel, and then I will make them available. But I promise I will. Okay. Cool. All right, your 30 seconds are almost up. All right, let's get started. Okay, so this is a fun little D3 thing that we made to sort of prove to you that hypothesis testing is important. You can change the means and the standard deviations and the number of samples and see the p-value and if it's significantly different. And that's all a lot of fun, but I think that's not what you came here for, so we can all click next. Okay, so the first test, and now this is where it's going to get interesting, and we're going to be switching back and forth. Okay, so, no, I want this in presentation mode. Okay, so the first thing that we're going to do is a one-sample t-test. So t-tests, remember, if we remember our grid, are for numerical data, and this is when we're comparing against some sort of an ideal. So we use this when we're either comparing to targets or comparing to a known value. The function that we're going to use, we do from SciPy.stats import t-test one samp, and the arguments it takes are a vector with our observations and then the actual expected mean that we want to get from it. It's going to return two things, a t-statistic and a p-value. You don't care about the t-statistic, you only care about the p-value. That's the thing that you want to be less than 0.05. Okay, so you can all see that there's a whole story if you want to read, but what might be better... Oh, I have to reset this. There we go. Okay, cool. So, for those of you... Who here has used Codecademy before? Okay, a lot of you, but not all of you. So the way Codecademy basically works is we type into the center. This is our code editor. It's set up to be a little bit like Vim or Emacs. And then we click run when we think we have the answer to the question. And if we do it right, this little guy will turn green. And sometimes we'll even see things show up in this part of the screen. Sound fair? Okay. So let's all take a moment and work through question 1 together. Isn't this fun? It's like being back in school. Okay, so we have a small data set called ages. We can even print it, take a look at it. And I think that was actually the first thing you were supposed to do anyway, so that's good. Okay, so what do we think about the size of this data set overall? Do we think this is representative? Is this like a good size to be working with? Probably not, right? This is more of a toy example. Generally, when we're running t-tests, we're hoping to have a lot more. But it's not completely crazy to have a data set like this. So for instance, a lot of times if you're looking at something like revenue over time, your company, you might be working at a startup, you might only have 12 months of data, so you might be working with a size like this. It just means that you're going to have a harder time knowing if any change is significant. Okay, so first we're going to calculate the mean. I've never done a talk like this, so I don't think it totally works for me to be narrating the entire thing. I think we should sort of all work a little bit independently and then come back together just to discuss. Does that seem like a good format for this? Okay, I'm just taking that advice from my friend that you guys are all really silent when you're happy. Okay, so what do we all think? Is this difference significantly different than 30? No. Okay, our p-value is 0.56. That's too high. And let me just print the mean really quick. Okay, yeah, so we can see that even though the mean is indeed higher than 30, our p-value isn't significant. Now, that doesn't mean, just because it isn't significant, that doesn't mean that it's not true. In this case, I think in our scenario here, we're monitoring the ages of users. It's possible that we just haven't gotten enough data yet, and that as we get more and more data, then we'll want to be doing this. Cool. All right, so let's talk about, let me make sure that's actually the next thing here is two sample. Oh no, we keep talking about one sample. Oh yeah, this is fun. I should really remember what goes on in this since it's my own thing. So this is actually a fun way if you're ever sort of unsure about if you're using the correct statistical test or not. I really enjoy making up sample data and sort of getting a feel for how the t-test will actually operate or whatever statistical test you're using. So in this case, what we've done is we've created 1,000 different sample data sets. And what we want to look at is how many of them end up being significantly different. So we have basically just a great big two-dimensional array where each row is one of the different samples. We generated all of these just using np.random.normal. So we can run that here. So you can kind of get an idea from looking at all of these that sometimes it's significant and sometimes it's not. And this is really getting at the definition of what a p-value is. So what does it mean that p is 0.05? It means that there's a less than 5% chance that this happened by accident. And another way of thinking of that is if I had 100 random samples under the same conditions, 5 of them would be significant even if the overall distributions were the same. And that's going to become very relevant later when we talk about comparing more than 2 samples when we get to ANOVA. And I did get through all of them. Oh, okay. Now I have to do this. I really should have this in God mode while I'm doing it. So we happen to have one where exactly half of these were valid, which is interesting. Okay. Okay, so let's talk about 2-sample t-tests. So 2-sample, just a little bit more complicated than 1-sample. It's when both of your data sets are experimental. This is one of the easiest ones to run. You just put the 2 different distributions in. It shouldn't matter what order you put it in. It shouldn't say t-sample 1. It should say t-sample independent. That's annoying. Or t-test end. But we just plug in our 2 distributions. Now this is going to by default do a 2-tailed test. Does anyone know the difference between a 2-tailed test versus a 1-tailed test? Does anyone want to raise their hand and tell us? Yeah? You're the only one who wants to raise your hand here. He did. Oh, go for it.
So a 2-tailed test, we'll be looking at
Okay.
rather than on only one side of the distribution.
Okay, so what does that actually mean in practice? Yeah, you want to go for it?
If you're looking at, for example, at the mean between
Mm-hmm.
we might want to say if it's 0 compared to its greater,
Mm-hmm.
or also greater or equal.
Mm-hmm. Yeah, so a two-tailed test basically says, I don't care if it's greater than, if sample 2 is greater than or less than sample 1, I just want to know if there's a difference. A one-tailed test is where we say, I know that if they're different, it's because the second sample is going to be greater, or the second sample is going to be less than. And the reason you would use a one-tailed test is it makes it a little bit easier. It divides what you need by 2. So something that is not significant in a two-tailed test can be significant in a one-tailed test. And the trick is knowing which of those is valid. So for instance, did you have a really good reason to believe that it should be one-tailed, that if there was going to be a difference, that it would absolutely be a greater than? Or are you really just looking for any difference and the direction doesn't matter? Okay, so let's give that a try here. And it's still not resetting properly? Cool. Okay, so in this case, we have two different vectors representing 2 different weeks and about the amount of time spent on a website, so we can really quickly calculate the mean. Okay, so looks like they're different. Anyone have any ideas about, before we even do hypothesis testing, what are some good ideas to try and decide if the means being different is real or not? What are some things that we might want to try before we even do a hypothesis test? Yeah, yep. Plotting the histograms. 2 good ways to do that. You can plot them on top of each other in Matplotlib, or you can use magical violin plots in Seaborn. Does everyone know what a violin plot is? It's really weird looking. So what it does is, you all know what a histogram is. It's really difficult to compare 2 histograms to each other. If you're using Matplotlib, you've got to somehow make them like semi-transparent, and then you probably want to normalize them so that they sort of look the same. And comparing more than 2 is really a mess because they're all on top of each other and it's hard to see. So what a violin plot does is it takes your histogram, it rotates it by 90 degrees and doubles it because symmetry is pretty. That part I never really got. It doesn't have to do that. And then you sort of have them plotted next to each other like bars. And it makes it really easy to see if your histograms are different. That's particularly important to do before doing any of these t-tests because these only work if our data is quasi-normally distributed. And we'll go into detail a little bit later about what that means because obviously most data isn't normally distributed, right? Most data has some sort of skew in it. Does everyone know what normally distributed means? Does anyone want me to go over that? Yeah, awesome. Cool. Okay. I'm going to keep working through this. We've decided we're all going to work a little bit independently on this because it's very boring if I just narrate typing. But this way, everyone at least gets to practice. Okay, so has everyone gotten to the point of calculating the p-value? Is it significant or not? is it less than 0.05 or greater than 0.05? Again, you're very quiet, and I have been told that means that you love this talk. So our p-value, as we can see up here, is much less than 0.05. That means that we're in good shape here. Any idea if y'all forgot at some point which came first as the output, the t-stat or the p-value, how you could kind of eyeball it and tell the difference? The t-stat is always going to be like a big number generally. It's generally going to be, greater than 1 or, great absolute value greater than 1. Your p-value is generally the thing that's going to be, hopefully, if not less than 0.05, in the neighborhood of like 0.2, 0.3. Okay, so this is where things start to get fun, is talking about the dangers of multiple t-tests. I am going to just sort of go off script and talk for a while because this is something that I actually feel very passionately about. So who here has heard of the reproducibility crisis in biochemistry? Yeah. Can you tell us a little bit about what it is? Yeah, basically a lot of pharmaceutical, so I used to be in drug development. The way that drug development tends to work is that the basic research isn't done by the drug companies, it's done by research labs at universities. So the universities go, they try and figure out if something's true, they publish it with p less than 0.05, and then the pharmaceutical companies say, okay, you've told me that this protein, if I can just find a drug that makes it turn off, this is the right protein to cure diabetes or to cure Alzheimer's. And then they'll go and actually, try to make a drug for it. But more and more, the companies have been trying to reproduce the results that were done at universities and found that it doesn't work. Now, a hint to why that might be a problem, and we'll get to this a little bit later in the talk, is if you just look at all of the reported p-values in research and you plot a histogram of them, you'll see there would be sort of a peak right at 0.049. And that's because people don't publish things that weren't significant. You can't say, well, I found out that this particular drug is like really bad and doesn't do anything. So people tend to keep running their experiments until they can get to a 0.05. And basically, anytime you're running lots and lots of hypothesis testing, you can start to get into trouble. I actually I'm going to just skip ahead because I really like this slide. Okay, does anyone read XKCD? I really hope that many of you do. Okay, so this is a great cartoon. It's kind of hard to read, but it's about jelly beans. So here what we have, this is actually a perfect demonstration of why we need to use ANOVA. So here we're saying, hey, jelly beans cause acne. Scientists, go investigate. And they do it for all colors of jelly bean, and they say, nope, there's no link. And they say, well, maybe it's only certain colors. So they test every color. And you can see here, they finally get one result that's less than 0.05. Now, if we think about it, yellow was not the best color for this, but there are exactly 20 of these experiments, and one of them had p less than 0.05. That's exactly what a p-value tells you, right? Is that 5%, 1 out of 20 experiments, even where there is no real difference, will magically get this. And that's why you want to be really careful about running lots and lots of t-tests. So what's the solution to that? Solution is something called ANOVA. So ANOVA is a different distribution. You don't have to worry too much about what's going on under the hood, but it's something that is going to allow us to test the difference between lots of different data sets without running into this problem. Now, what's very confusing is it's not called ANOVA in SciPy. It's called F one-way because the distribution it uses is called an F distribution as opposed to a student's T distribution. And you'll notice instead of getting a T stat out, we get an F stat out. But it's basically the same thing. So I really should have gone into God mode. I actually have to do all the work on this now. Oh, no, I don't. Great. Okay. So we run ANOVA, we do ANOVA, and it's just going to give us one p-value back, right? So we've compared all these different distributions, and all it said is, yes, your p is less than 0.05. But that doesn't actually tell us which of the distributions is different. And so in order to do that, we're going to need another hypothesis test called 2 keys, which is a funny name, so we can take a moment to laugh at that if we want. But apparently, that is not the order that we teach this in this class. First, we talk about assumptions that we need. So this is cool, so we're going back to this. Okay, so remember when I talked about plotting those violin plots or histograms and that they're a good idea? They're not just a good idea to get a ballpark of whether or not there's a significance, they're also really important for our assumptions. And this is like a particularly big deal with ANOVA. T-test is a little bit more resilient to funny data. ANOVA, you really do need for your data to be normally distributed-ish, and mostly that just means that it's not bimodal. And where this can get really tricky is if you have a relatively small sample set. So if you have a big data set, it's very easy to plot the histogram and be like, hey, that data is bimodal. But if you're working with a smaller data set, it might not be super obvious. So that's when you have to really think about what your data is and say, is this something where I reasonably believe that it should be normally distributed, or is it something where I can imagine it being bimodal? So an example we give here is like traffic times, peak traffic times. This is true both of like actual traffic, through a stoplight, but also traffic to a website when you're doing A/B testing. It's not entirely unreasonable to think that there might be 2 peaks, a morning and an evening peak, which would make ANOVA not work. The population standard deviation should be equal-ish. Generally, the way we test for that is we just take the ratio and we're looking for something, between 0.8 and 1.2 so that they're sort of close, but they don't have to be on top of each other. The samples must be independent, and independent means knowing something about one of them shouldn't affect another one of them. So good examples of this is basically if it's the same people in the data set. So if, I know that I'm comparing a before and after, ANOVA is actually not the best way to do that. Okay, so I'm going to skip ahead to actually get to the thing that is cooler than ANOVA, and that's 2 keys range test. So 2 keys range test is cool. It is not in SciPy. This is the only thing I'm going to teach that's not in SciPy. It's actually in stats models. And what's really nice about it is it tells you exactly which of your pairs of data set is the one that's different. If I just keep pushing run, it'll eventually just give me the answer. Oh, that's another fun thing. If you keep pushing run enough times, it'll just tell you the right answer. No, but it won't for me because I already put in the things. All right. So this is an important part about how 2 keys range test works. It's different, so because it's stats model and not SciPy, the arguments are a bit different. So instead of notice how when we did ANOVA, which is cleverly named F1 way, we put in the 3 separate data sets and then we just run it. For reasons, the way that 2 key works is you actually have to make it into one set of one data set with labels. So if you're using pandas, this is really easy. If you have, a column of labels and then a column of values, you're in really good shape. If you're not using pandas, if you just have loaded in 3 separate CSVs, it's a little bit annoying because you'll have to create a vector of labels. But once you have that, you can just do pairwise. And then the final argument you need to give it is your significance level because, again, it's going to be doing all of that stuff for you, and rather than giving you back individual p-levels, or p-values, it's going to give you yeses and nos. So you have to tell it what threshold you want to use for yeses and nos. Again, we generally use 0.05. If it's something that doesn't matter a whole lot, you can use 0.1. If it's something that really, really matters, like you're working on like a space shuttle, and if you screw it up, people are going to get blown up, maybe you want to use something like 0.01. So you run this, and what's really nice about 2 key is it is by far the prettiest output that we will get. Okay, well that was less pretty. So, yeah, so what's really nice here is it actually just gives you this little reject thing. And what is it talking about when it says reject? It's talking about the null hypothesis. Are we rejecting the null hypothesis and saying that groups are different? So here it's saying A isn't different from C, B isn't different from C, but A is different from B. This is actually can be a really interesting thing that you end up with. When we get to the A/B testing part, I'm going to talk a little bit about kind of a crazy A/B test that I ran. Because if you think about it, it's kind of weird. You think of like the transitive property in mathematics, right? If A isn't distinguishable from C and B isn't distinguishable from C, how can A not be distinguishable from B? Well, it's because they're a little bit further apart. You can kind of imagine you've got A and B and then C. So A and C are further enough apart, but B is kind of in the middle. Cool. Okay, so now we are getting into the categorical test. So if we think back to, or if we just look back, because we can go back like that, now we're into that categorical column. So that's a lot of times, I think, what you're more likely to see with A/B tests. You could do a binomial test. You can do, if you are comparing against a known quantity, or a chi-squared test if you're comparing multiple data sets against each other. Chi-square is interesting because it actually will work with more than two samples. It has that correction in it. Now, there's something else that's called, oh gosh, I'm blanking on it. Yeah, Fisher's exact. So if you have very small data sets, chi-squared will have more errors, and you'll want to switch to Fisher's exact. Luckily, the SciPy chi-squared test actually has that as one of the keyword arguments. But generally, most people don't need to use that. Most people are good with just using chi-square. But first, let's talk about binomial. So binomial test, we're comparing against a target value again. You can read this, but I'm going to talk a little bit about, while you guys work through this example, I'm going to talk about another example where I used binomial test, which was sort of interesting, which is in a pricing test. So we were experimenting with microtransactions. We wanted to make certain lessons that people would have to buy instead of having them just be available for free. So we were trying to see, if we were going to do that, what should we price it at? Should we price it at $1.99 or $3.99? And it was funny, this actually happened on a day when I was kind of not paying attention. I was kind of busy with other things. So a product manager came to me and said, hey, I'm running a chi-squared test. Can you please show me how to calculate it? And I said, oh, sure. I pulled up my notes from this. I showed him how to do a chi-squared contingency test and walked away. And then about an hour later, I realized that I didn't trust him. So I came back and I'm like, hey, Brian, what were you testing? He's like, oh, it was great. I was doing this pricing test, and what do you know? More people clicked on it when it was $1.99 than when it was $3.99. And as scientists, we should all facepalm a little bit because, of course, more people will click on a cheaper thing, but that's not really what we want to know. What we want to know is, are you actually getting more overall money? And there's a couple different ways that you can test this, but binomial can actually work really well for this. So what you can say, rather than saying, like, I want to compare the percentage of people who clicked, you can say something like, well, I know it's going to cost us so much to build out this feature, so I know that I need some minimum amount of, money that I have to make per month. So maybe you say something like, I need to make, I'm just going to use round numbers to make it easy, I need to make $100 a month. And if you're selling it for $1.99, well, that means that you need about 50 clicks, versus if you're selling it for $4.99, that means you need about 25 clicks. So you can look at your monthly traffic and figure out what those two percentages are and use the binomial test to compare the actual values against that minimum amount that you would need to be able to justify the test. And that's actually a really good use of a binomial. So instead of comparing the two numbers against themselves, you compare them each against the target. And once you're sure of that, then you can start doing things like just doing regular multiplication and saying, how much profit am I actually getting from each of these? But yeah, I think this is a really good story because it reminds us that we can know all of these tests, but what matters is, not thinking of them as scary math, but thinking of them as common sense and things that we have to always be using our non-math brain to think through. Okay. So here's the actual chi-squared test, and it's called something called chi-2 contingency. It's also imported from SciPy.stats. It's also slightly different because, we have to make things complicated, otherwise it would get boring. So for chi-squared tests, we have to actually build a contingency table. And I'm actually going to pull up an online, so there's a lot of really good online chi-squared tests. You don't have to do it in SciPy. I like to do it because SciPy doesn't, go offline. But if I look up, so this is a really good one, and the reason I like it is it lets you interactively build your contingency table, and it's far too small for you to read. Yeah, that looks reasonable. And it makes you really think about it. So with A/B testing, a lot of people will do this wrong. They'll say something like total visits, and let's make this nice. Total number of visits, and this will be something like total number of purchases. And they'll have, control and variant. This is actually wrong because the contingency test, what it's supposed to do is take all of the people who visit your site and divide them into buckets. So the total number of things in the contingency table should add up to the total visitors. So instead of this being a funnel where you sort of have 100% of people in the first column and then some percentage in the second, this should actually be number who didn't purchase. And it would look something like that. I actually find this quite helpful sometimes instead of using the SciPy test because it forces you to write out your thinking in a way that it's very easy to not do when you're just making a NumPy array. But anyway, you do that. This one has 4 outputs, which is super exciting. The second one is the one that we actually care about. And in this case, it wasn't significant. And it's not letting me go on to the next one because we're at the final exercise. Excellent. Cool. So now we get to the fun stuff. Okay. So we've learned a whole bunch of different statistical tests. We also know when to use them. Now we want to get into sort of the so what, the bigger experimental design questions. So generally, these are the rough steps that we want to go through when we're doing an experiment. And I think it's really important, even if you're working at a company and doing A/B testing, you should still be thinking of this as a scientific experiment. So that means that the first thing you should do is state your hypothesis. What do you think is happening? This is really important because a lot of times people go into A/B testing without fully thinking through what they think is going to happen. And that determines everything from what type of hypothesis test you should use. So like that example where we talked through the pricing test, or when we talked through if you should use one-tailed or two-tailed. It also determines what the best metric is that you should actually track. Picking a metric is really important. So for instance, one thing that we did once is we were, is everything okay? We wanted to know which course we should build out next for Codecademy. So we sent a bunch of emails out to people, saying, hey, we're thinking about offering, course X. And they would click on a link and they would go to a page and it would tell them a little bit more about course X that we were thinking about, and then they could add their name to a list if they were interested. And some people were sent to course X, some people were sent to course Y, some people were sent to course Z, etc. And the idea being that we could do this massive comparison and decide which course was the most likely to get the most people to sign up for it. And what's interesting there is there's a whole bunch of different metrics that you could use. You could use the entire conversion rate from number of emails sent to number of people who actually, at the end said, yes, I want to take this. You could use percent of emails opened. So did, the subject line of we're thinking about teaching course X, did that make people sign up? We could use from once they've opened the email to once they actually said they were purchased. There's a whole bunch of different things. And having a clearly stated hypothesis lets you decide which of those you think is important. So for us, we decided that the email headings were all weren't really testing what we wanted. They were kind of just testing one, word, because you can't put that much description. And we really wanted to know that once people had read through the full description, the full syllabus, did they decide to convert? So that was a different metric that we used. It was also conveniently, because that was a higher percentage, it meant that it was easier to get to significance. So in general, the higher your conversion percentage, the easier it is to get to significance. So, and that's because it's very hard to tell the difference between 0.01% and 0.001% when you have a finite number of samples, because they might both look like 0 people clicking with a small sample size. But if you're trying to compare 20% to 25%, or even 20% to 21%, that's a lot easier to observe the difference because you're going to get more people clicking. Anyway, so we pick a metric. We calculate the metric for the control group. So this is really important because it means we need some information going in. So for that example I was talking about, we want to know just ballpark what percentage of people click emails. Are we talking 1% or 20%? Turns out it's far less than 1%. Nobody likes to open their emails. Once we know that metric for the control group, then we want to find the smallest difference that we're able to detect. And the reason that we do that is it lets us know how big of a sample size we need. So, like I was saying before, just because your results aren't significant, that doesn't mean that you did the test wrong. That might be the correct answer. But in order to know that you've run it long enough that you've crossed that threshold from I just don't have enough information to I have enough information to say that both of these groups are equal, you have to be able to do a good sample size detection. So the smallest difference you want to be able to detect, the way I generally explain this to product managers is, if I told you that, 1% more people signed up, is it actually worth it for you to build out this new feature that you want? What is the difference that actually you would bother telling your boss about? And that's your minimum detectable difference. So let me just show you another website that lets you do this calculation. So this is Optimizely. It's available for free. It lets you calculate sample sizes. You start with this baseline conversion rate. So in our example before, that's the number of people who open their emails. And then you put in a minimum detectable effect. So this 20% would be 20% greater than 3%, which would be 3.6%. And then the amount of statistical significance. And then this just tells you the ballpark of how long you're going to have to run your experiment in order to get to a point where you think it's reasonable, where if the answer is not significant, you can say, okay, that was a real answer. Okay, so this goes into that a little bit more detail, like what do I do if my results aren't significant? Does it mean that I'm a horrible failure as a person and have done my experiment wrong? And I think if you've all been listening, the answer is no, that can be totally fine. There's some nuance to what it means exactly. It doesn't just mean there's no difference. It means the difference between those two things is smaller than some amount. That amount, if you're doing this right, is that minimum detectable difference that you put into the sample size detector. So for instance, if you had an experiment like this and you had 12,000 samples pulled per variation and it was insignificant, it means that the difference is going to be less than that 20%. And hopefully you've chosen your minimum detectable difference such that you don't care if the difference is less than 20%. They're essentially the same to you. The really important thing is it doesn't mean that you need to run longer. It doesn't mean that you should keep going. And in fact, that can really endanger your experiment because it's not like you have perfect data that's always generating the perfect numbers. There can be random variations, and you might momentarily reach a point where there's significance and then goes away. And so you're actually biasing. So when we talked about the reproducibility crisis, a really common thing that people will do is say, ooh, I'm at 0.08 for my p-value. That's really close. Let me run another replicate and see if I can get to 0.05. And they'll run just until they get to 0.05, and then they'll stop. And although it seems like that's okay because they've done a significance test, it's actually a problem because they're not going to keep running after they hit 0.05 and risk it going back up again. So they've actually created a biased flip of the coin, if you will. Yeah. Okay. So we finished up a little bit earlier. If people are interested and want to learn more, we have a whole line of courses on these topics. We have an introduction to data analysis, which this course that you just took is part of. We have Learn SQL from Scratch, which is a really great way to learn SQL for data analysis, and it's very focused around business cases and business metrics. And then we have data visualization with Python, which focuses around matplotlib and Seaborn. So you can learn how to make those cool violin plots that are the histograms turned on their side and look all pretty. So what questions can I answer for you about statistical significance? Okay. Yes.
I don't know how to ask because I have come across all these like t-tests, p-tests before, which is like for me is always I don't understand. Is are you comparing two samples of population together, or like it's always like confused me quite a lot. Like about are you comparing two mean value, but you're not comparing like I just don't get it.
Yeah. That's a great question, and that's how I used to feel about this until I made this chart. I feel like it's really important to be able to sit down and think about these different things. So sometimes your data is numerical, and you're comparing two means together. So some examples of that would be I'm comparing blood pressure. I want to see if blood pressure changes when I apply a medication. Or I'm comparing scores on an exam. I want to see if some people score higher on an exam than other people. Those are things where we're in that numerical category. Categorical is really tricky because a lot of people don't realize that they have categorical data. Categorical data is whenever you have a percent and you're comparing different percents with each other. So examples of that would be number of people who click a link to a website. Even though you're looking at a number, you're really talking about a percentage, and you want to see if the percentages have changed between your two different experiments. Also, this idea that you can be comparing different numbers of things. You can be comparing against a known target, or you can be comparing two different examples to each other. Does that help?
I'll have to do some more research.
Yeah. Yeah, I'm trying to think if there's anything else I can say about that. Yeah?
With the t-test and ANOVA, you suggest that they need to be normally distributed, your data?
Ish.
So what non-parametric tests would you suggest to use in those situations?
So I think it depends. I think ANOVA is actually relatively robust to things not being normally distributed. The thing you really have to look out for is bimodal data. And when you have bimodal data, I think a lot of times you actually should be saying, do I really want to be comparing is this really one data set or is this two different data sets? And you might actually want to end up splitting those out and ending up comparing three things rather than just comparing a bimodal data set to a univariate data set. Yes?
So if for technical reasons you can't split your population in half, so instead you compare week 1 to week 2, how do you stop other things like seasonal effects and other impacts in your site?
That's a really excellent question. The short answer is you can't. The long answer is, I think for things like seasonality, you look at the past years, you look and see what those trends are. And you can actually do something like maybe instead of comparing week 1 to week 2, you compare the difference between week 1 a year ago and this year and week 2 a year ago and this year. So I did something a little bit similar to that. So when I was working at the educational technology company, we didn't have access to test results. We couldn't test people on a cumulative exam. What we did have is successive homework assignments. And we wanted to look at, did people do better on homework 2 after having had an adaptive intervention after homework 1? And that was a really interesting case where, we would expect some change between homework 1 and homework 2. I guess that one we did have a little bit of an A/B test in that because we did have some people who hadn't had the information. But still, we had to compare a difference, two sets of differences rather than comparing two individual measurements. So I think that's a good way. I think it's also just really important to be aware of what else is going on, because sometimes, if you look at your data over time, you might say, actually, week 1 and week 2, there shouldn't be a big difference between them. But if you know that like another person at your company is also running an experiment, that's like a big problem. Like you're not going to be able to decouple those. And then a final option that you could do is, rather than comparing week 1 to week 2, compare like weeks, 1 through 10 to week 11. And you can do something like take a whole bunch of data. You can either like do a novas and compare all, or do 2 keys and compare all of them. Or you can do something like, say, I have so much data from week 1 through 10 that I'm no longer doing a 2-sample test. I'm going to consider week 1 through 10 to be a known quantity and do the sample versus known quantity. Yes?
I've been in this situation like you many times. For example, when the IT development, it's too expensive to have two variants in one time. So they make the change in a specific time. So there is no place for A/B testing to run at the same time. And the good thing to kind of make result out of this change is to run the local impact. It's what is called it's R package from Google. You can download it, and basically what it tells you, it predicts the behavior from that moment into the future, and kind of compares what actually happened after that. There is some sort of significance level intervals from the statistical point of view as well.
Yeah. This is also another good example. This is like fake data, but if you can do more than week 1 and week 2, if you can have a bunch of data points before and a bunch of data points after, that works quite well. And we do that fairly frequently, because sometimes like pricing is actually a really good example where a lot of times you just can't do an A/B test because there'll be leakage between the two groups and people will know. The other thing that's just good to know generally, for if it's specifically A/B testing on like a website, there are more and more tools available so that you don't have to ask your engineers to build 2 versions of something. Like I think it's Google Optimize. You can tell it to go in and edit HTML for you, and actually like it sits on top of your website, and like we actually did use it for pricing tests, which is a little bit of a weird example, but like we actually edited the bit that said, it costs this many dollars to something else. Yeah.
I've seen that work on websites. Do you know if they have that for apps?
That's a good question. I don't know, because Codecademy doesn't have an app yet, but we're working on it. But I feel like there's got to be, especially like if your app is like built in React or something like that, that's not so different from, the regular internet. But if it's like an iOS app, it would have to be something more specialized then. But yeah, I don't think it's necessarily bad to compare week 1 to week 2, as long as you fully understand what's going on, and that there isn't something else big that happened, that you're not, for instance, comparing a random week in July to the week before Christmas. I think it's fair. Another thing that we've started doing just generally to make sure that we're not stepping on each other's toes is make sure that we have a running document of what experiments are being run. And we're pretty strict about telling people, like, if something is not an A/B test, if it's a week over week, we'll keep other people, we'll have a freeze on releases for those 2 weeks and say you can't do anything because we're really trying to measure this one quantity. Other questions? Yeah?
You said in the experimental design about choosing the metrics that you want to measure. Is
Yeah. That's an interesting question. It depends on what information you have going in. So if you've varied something before, so for instance, if you know that this, so I'm trying to think of a good example of this. If you know that you've had different prices at different points in time or something. I'm stuck on pricing tests because that's what I'm thinking about. But I think a better example would be if you have something like if you're in economics and you have a lot of natural experiments happening. So for instance, if I don't know, if you're looking at sales on rainy versus clear days and you know you've had it before, you can probably do something like PCA to get like a dimension that has the maximal variation. But I think in a lot of cases, the reason you're running a test is because you don't have data on it. And then what I think is really important is spending a lot of time talking to, if it's a UX designer that's making a change, if it's a product manager that's making a change, and really understanding what you believe you're doing. So for instance, a conversation I've had, actually, so this was a thing that happened a lot. A lot of people pick metrics that are way too macro. So they'll say OKRs are a thing here in England, right? I'm not crazy when I'm saying OKR. Good. Okay, so I think of every OKR as basically a little mini experiment. And people will say things like, well, I want the KR for my, small engineering team to be money made by the entire company. And say, that's bad because so many things are going to affect that. And so I try to, when we're doing quarterly planning, I schedule meetings with every product manager and really try to drill in on, okay, what is it that you think you're doing? Oh, you think that you're going to be sending alerts to people telling them that it's been so many days since they've been on the platform. And your hypothesis really is that you're going to increase engagement. And even more than that, you're going to decrease the number of people with more than X days of inactivity. And so trying to get at something really, really specific that actually tests the thing you're changing. And I think that is a better practice for it's funny, this is actually a thing also in biology. It's called the difference between, it's been a long time since I did biology, but for instance, you can test, how a drug binds specifically to a molecule, or you can test the overall effectiveness of, whatever the process is. And you can do the same thing in, engineering a website. You can either test the actual thing that you think you're doing versus testing that the thing you think you're doing actually affects the bottom line. And I think it's important to sort of do both, but a lot of times you can't get at that overall, did we make more money because of this, without first establishing that the thing happened, if that makes any sense. Other questions? This is way more fun than doing math on the website, I think. Yeah. Oh, yeah.
Have you had an experience using more Bayesian techniques with A/B testing, especially when if you have small sample sizes?
Yeah. No, because I can't convince anyone to build a system so that I can do multi-armed bandit. But I've seen people do that. It's really cool. It's much more on the sort of engineering side of things, of getting them to build does anyone know what we're talking about? Has anyone heard of Bayesian approaches to survey design or to experimental design? So there's this concept called multi-armed bandit, and I am led to believe that the reason for that, the situation that it's based on, is you walk into a casino with those slot machines where you pull the arm, and apparently they were called bandits, and you think that one of them is better than the others, and you want to optimize between exploration, so trying all of the machines, and exploitation, spending the most time on the machine that is the best. And this is actually very relevant to A/B testing. It's also relevant to you can think of lots of situations where the goal is to get to the best thing as quickly as possible. And so there are, I took out my slides on Bayesian statistics. That makes me really sad. But there are methods where you basically start by saying, overall, this is my expectation of how it works. I'm going to start by equally pulling on all of the arms or equally testing each thing. And then as one starts to look a little bit better, I'll start driving more of my traffic to the better one. And not only is this good, it's really good when you have lots of options. And not only is it good because it's maximizing whatever the good thing is, but it's also good because it takes fewer samples to prove that things that are really different are different from each other. So for instance, if one of those slot machines was just terrible and never paid out, you can prove that very quickly, but it takes many more samples to prove that two things that are close to each other are different. And so you're driving all your traffic that way. Again, there are a lot of platforms that will do this for you, because the bigger challenge, the math isn't super hard, you can Google it. It's much harder to build the actual engineering system and convince your engineers that it's a good idea. Does everyone know what Bayesian is? Because there's a really good XKCD cartoon if anyone wants me to explain it. Yes? Okay, cool. It's a really good, okay, so. Okay, so this is my favorite way of explaining this. So, super funny cartoon. So they've got a little machine here, and it's going to tell us if the sun exploded or not. And it's going to take a measurement, and then before it tells us the result of the measurement, it's going to roll 2 dice. And if it happens to roll 2 sixes, it will lie to us. So in this case, it rolls the dice and it says, yes, the sun has exploded. And the frequentist statistician says, well, it's pretty unlikely to roll 2 sixes. That's p less than 0.05. Therefore, yeah, the sun exploded. Whereas the Bayesian statistician says, bet you $50 it hasn't. So even if you don't know Bayesian statistics, you get this joke inherently, right? What is the Bayesian statistician thinking? That it's quite unlikely that the sun exploded, right? So that extra piece of information, knowing that the sun exploding is very unlikely, that's called a prior. And Bayesian statistics is all about incorporating a prior and then using new information to update the prior. So the other classic example of this is disease detection. So, for instance, if you're a doctor and you have a patient come in and you're testing them for a very rare disease, and you're testing them for a disease that only occurs in 1 out of 100,000 people, and you have a very accurate test. The test is correct 99% of the time, and you test the person and it comes back positive. You would think that means they have the rare disease. But what Bayesian statistics actually says is, well, the test is wrong 1 out of 100 times. The disease occurs 1 out of 100,000 times. Therefore, it's actually much more likely for the test to be wrong than it is that the person has the disease. So it actually tells you that you should perform the test until the error gets lower than the rate in the population. And then you'll be able to say, okay, now I have enough information. When I worked at the adaptive learning company, they actually also used Bayesian statistics in kind of a cool way. So another intuitive thing, if I have 2 students and I'm asking them maths questions, and I ask one student 1 question and he gets it right, and I ask another student 10 questions and she gets 9 of them right, we know inherently that for some reason I trust that 9 out of 10 student much more. I'm much more confident that she knows the material than the 1 out of 1 student, even though 100% is greater than 90%. So you can actually use Bayesian statistics to figure out what somebody knows, but you start with a prior of, I assume that, there's a 50-50 chance that they get the questions right. Or if it's multiple choice, you'd say something like, I assume there's a 25% chance, 1 out of 4, that they get the question right. And then you update it as they go. Did anyone here take the GRE for grad school? Okay, maybe it's an American thing. It's an online... It's an online, or it's a test that you take to get into grad school, but it's computerized, and people really hate it because it has a Bayesian model, and it will actually, as you get questions correct or incorrect, it'll start upping or lowering the level of each question to make it harder or easier. That was a fun little divergence. Any other questions? Okay, I think we're good. Thank you all for coming, and thank you all for wrapping up a little bit early. And just one more time, because my bosses will be very sad if I don't do this, 3 different boot camps available for $199, which is even less in pounds. There are between 6 and 10 weeks, require about 10 hours per week of work, and they're fun because I wrote them, and you guys have all had fun here.